Hello. Today we're going to talk about the way to actually compute a convolution integral. In this case, I want to do it with an exponential function and either a sine or a cosine. This is in the context for computing convolution integrals for Laplace transforms. And I'm fully aware that there's modern software that can knock this right out, but you should at least see how to do it by hand. So here we go. And let's get rid of this nonsense here. And so here's the convolution integrals that we're interested in. Now, the way I want to do this, and I want to get my screen set up just a little bit better than this, give us a little bit more room to work, is instead of doing these integrals directly, which involve multiple integration by parts, I know you do this in Calc 2. Instead, to do these, what I want to do instead is to calculate the integral 0 to t e to the au e to the I b t minus u du. And recognizing that before I actually do the integral calculation, using Euler's formula, what this boils down to is that this is going to be cosine of b t minus u plus I sine b t minus u du. And notice the real part will be the cosine, and the imaginary part of our final answer will be the sine. So that comes from the sine having the I attached. So I'm going to go ahead and do this integral instead of these two separately. And we don't have to worry about all the nasty by parts. And you do have to worry about my incompetence with this program. But let's go ahead and just get started on this integral here. Now we're going to start with this integral. And I'm going to go ahead and write this algebraically as follows. E to the au. I'm going to use the multiplicative properties here. E to the I bt times e to the minus I bu du. And then notice t is a constant with respect to u, so this can be safely taken out of the integral sign. And then we have e to the a minus ib u du. So we have this thing sitting outside. That's not going to cause as many problems as you might appear. This integral now is fairly easy to do. That's sort of the point of using the complex part, because that integral is a calculus 1 integral, e to the a minus ib u over a minus ib, evaluated between 0 and t. And if we plug in the t, first of all, let's pull this outside. That looks like it might be trouble, but it really isn't. And then let's go ahead and plug in the t. So we have e to the at, e to the minus ibt, splitting this up multiplicatively. Subtract, we plug in the 0, we get a 1 here. Okay? But this isn't that bad, because now when we bring this in to multiply through, we get this. So this e to the positive ibt times that, well, we just get e to the at there, which is really easy to evaluate, minus e to the ibt. Okay, so we're actually very close to being done. we still have to worry about this. So to get rid of this expression here, we're going to have to do a little bit of complex arithmetic. I'm going to go ahead and multiply by the conjugate. So what I'm going to do is I'm going to multiply by a plus ib. In the bottom, I'm going to have a plus ib, a minus ib. And then this other part just goes along for the ride. Now at this point, we may as well start expressing this with Euler's formula. So we now have cosine of bt plus I sine bt. Now, when we look at the bottom we have multiplying this, you have a squared minus iba plus iba minus iba, and then I squared is -1. So what we have on the bottom is we have a squared plus b squared. That's the modulus. We have that. And we still haven't done a lot of integration by parts, although we do have to do complex variable algebra. All right, now let's go ahead and start multiplying and separating into real and imaginary parts. We still have this product here. I mean, this factor, which really reminds me of a modulus of a type. Now, the e to the at, we have a e to the at plus I b e to the at. So that takes care of that. And now we have to do this multiplication. And this is the price you pay for not having to do all those integration by parts. But I still think this is, the arithmetic's a little easier. Now, this part isn't the way we want it. So we have this part. Now I'm going to put the imaginary part in blue, just so we can really see it. Now, we got this minus sign. Now, let's look at the real parts of this. We have a cosine dt. We have a times this. Then we have I times I, which is -1. So we have minus b sine bt. Now we got to get to the imaginary parts. So we have, let's make sure we have all this in the parentheses. So we have plus IB cosine BT, and then we have plus AI sine BT. Now we're ready to split into real and imaginary parts. So let's look at the real parts. And everything is multiplied by this. So we have a e to the at minus a cosine bt. Now I have to be careful here when I get this multiplication. I times I is -1. All right, so that's going to be plus b sine bt. Okay, this part right here is going to be the cosine part. And let's just bring this along. I know it's inefficient. Now we have, let's put our I out here so we can really tell this is going to be the sine part. So let's do that. And we have our I right here. So we have b e to the at. Now we have a minus b cosine bt minus a sine bt. So, well, we have our, now, so what this basically tells us, and I think we should, give ourselves a little bit of room here. But so what the upshot is that this integral, the cosine integral, what again, the way I had phrased it, well, see a to the au cosine of bt minus bu du is this. And the sine one, which is the imaginary part, and let's do that one in blue, is this. And that's going to be b e to the at minus b cosine bt minus a sine bt. All right, so we do have that. Yeah, so, and just to show off a little bit, and I'll have to redo this video if I got this wrong, we'll go ahead and take a look at the integral um, by actually doing these integrals with one of these calculators, and this is one of my favorite ones here. If you go ahead and try, this is an old computer here, but let's say this is e to the ax, use an x here, cosine of bt minus bx dx, and we're going to go from 0 here to t, and let's go on that. And I know this is a lot quicker, but we really ought to be looking at this a little bit. And we see right there, and we see that we get the definite integral is what we have right here. We have the positive b, the a, and the a for the e is positive. So the a for the e is positive, and a for the cosine is negative, we can see here, and the b sine b is positive. So we get the right answer, and we wish to go ahead and try to do this with the sine instead. And let's give it a go. And again, checking our work. And let's see right here, simplify, rewrite. And notice the coefficient for E is B, positive B, as it is here. And then the minuses for the A and B as they are here. Notice the negative sign. So in fact, if I made a mistake, I made the same one that the AI program made. So I think we're good. And that's how you can do the convolution integral if you wish to by hand. So thanks for watching.